Hello and welcome to our lesson on algebraically defined vectors, where we'll make a connection between the geometric definitions we talked about in the previous topic, and then add to that so that we can do some more analytical work and less graphical work, and less drawing these vectors out in space for future problems. So geometrically speaking, we said a vector is going to be depicted as a directed line segment. So this might be what your vector looks like, but we haven't seen it on a coordinate plane. And that's what we're going to do here to get our algebraic interpretation. If I was to take my geometric vector and put it in a coordinate plane, so that its initial point is at the origin, we're going to call that a position vector. So we're going to position our geometric vector so that, again, its initial point is at the origin of our coordinate plane. So if I was to draw this position vector in here, maybe I draw something like this. Okay, so I'll say this is a position vector. I'm just going to call this vector u. Okay? Now, if I look at the end point of my position vector, the end point of that position vector has a set of coordinates. So if I look at the end point here, okay, the coordinates here would be however far I moved along the x-axis to get there and however far I moved along the y-axis to get there, right? So I have this horizontal component and I have this, oops, turned on my eraser. I have this vertical, did it again. Sorry, my horizontal component and I have this vertical component here. So I moved this far along the x-axis and this far along the y-axis to get to those points. Okay, so that coordinate there, again, we're always going to start our position vector or our geometric vector put into our coordinate plane at the origin. So where it lands, those coordinates are going to be what we use for the algebraic representation. So the endpoint of our position vector, again, it shows horizontally and vertically how much we've moved. So we can call those the vertical or horizontal components. And that endpoint at x and y, again, that ordered pair is going to represent the algebraic depiction of our vector. So geometrically, what we're looking at is, again, a directed line segment. Algebraically, what we're looking at is an ordered pair. Now, to distinguish between just some ordinary ordered pair and an ordered pair that represents the horizontal and vertical components of a vector, we use slightly different notation. And we call this component form. So in component form, we say that if vector u ends at the point xy, which is precisely what I showed you in the picture there, then we are going to define u as the component vector form x comma y. So we use these sort of triangular looking beginning and end, like parentheses, brackets, I don't know what you call them, but we close the coordinate with those. They look like greater than or less than symbols, but those will be the symbols we use to say that that ordered pair is not just any point on a coordinate plane. It is the terminal point of a vector. Okay, so in this picture, again, we could call u, we could say that the vector u is defined by the component form x comma y, which just means that is the point where the terminal, or that is the location of the terminal point of that vector. Okay, so I feel like I'm talking in circles, but hopefully that makes sense. So if a vector, again, is in that geometric depiction, it's just your directed line segment. Algebraically speaking, we're looking at an ordered pair. We're just using these different symbols to say that that ordered pair, again, is not just some random point on a graph, but it's the end point of a vector. Now, what if we're looking at a vector on a coordinate plane, but it doesn't start at the origin? It's pretty simple to still get a component form, and we can do this by counting the vertical and horizontal components from the initial point to the terminal point, and I'll show you what I mean with an example in just a second. So let's look at these three vectors. We're going to try to write the component form for each vector. So the first one is a position vector, is starting at the origin, And so the endpoint here, represents the component form. So we are going to move 2 along the x and 5 along the y to get to that endpoint. So we would say for this vector u, its component form would be 2 comma 5, with again the different notation to say that's not just a point but it's a vector. And then if we look at the second vector, again, it's in position. It's a position vector. It's starting at the origin, and its end point here is at the coordinates 3, -4. So horizontally moved 3, vertically moved down 4 to get there. And so we would say this vector's component form is 3, -4. Now, if our vector isn't in position, so the initial point isn't at the origin, then I can't just take the end point, take those coordinates. In this case, the coordinates would be -4, 0, and define my vector that way. If it's not in position, then instead of just locating the point, we actually have to count vertically and horizontally how much we've moved. So basically what we're going to do is pretend like this is our origin. From this new initial point as like an origin, I would have to go left 2 and I would have to go down 4 to get to my terminal point. So that left 2 and down 4 would be the component form for this vector. So I would say w would be -2, -4. So you're still gonna you're looking at the same thing. It's your horizontal and vertical displacements, but if we're starting at the origin, that endpoint counts those. If you're not starting at the origin, then you have to count them instead of looking for that endpoint. Okay, but it's the same concept. And think about this. What I'm saying here is if w did start at 0, 0, and so I'm going to extrapolate my picture here a little bit. If I started at 0, 0, and I went left 2 and down 4, that this would be how that vector would look, and that is equal to the vector that's in my picture, right? Those two vectors have the same magnitude and the same direction. One's just starting at the origin, the other is starting at -2, +4. Okay, so same vector again, just use your initial point as your start and count how far left or right, how far up or down are you going to get to that terminal point. And when you're counting, so you always start at the initial point. If you're going to go left, then your x value should be negative. If you're going to go right, your x value should be positive. If you have to go up, then your y value should be positive. If you have to go down, your y value should be negative. So hopefully that makes sense. Okay? Now we're going to try some vector operations, and I put a box over here that is giving you some of the details pertaining to those vector operations, but in my opinion these are pretty intuitive, so I'm going to reference that box in just a second. But if I asked you to just add two vectors u and v, we're able to do this geometrically using our parallelogram rule, but we don't need specific measurements. Here I think it's a little bit simpler and again a little bit more intuitive to add our two vectors. If I said add u plus v, I'm not sure what your intuition would tell you to do, but hopefully it's saying add the corresponding parts. So add the horizontal components and then add the vertical components. And that's precisely what we would do, and that is what this little box says over here. If we're going to add two vectors, so a vector given by a, b, and another vector given by c and d, where a, b, c, and d are all real numbers, so numbers are points we could find on the coordinate plane. If I wanted to add these two vectors together, I would take the horizontal components and add them to get the first component here. I would take the vertical components, b and d, and add them to get the vertical component in my answer. So remember, when you add two vectors, your answer is still going to be a vector. You're just going to add the corresponding components. And that works the same for subtraction. So if it's a vector minus a vector, your answer will still be a vector, where you take a and subtract c. That's what you see here. And you take b and subtract d, and that's what you see here. But again, that's just horizontal components going together, vertical components going together. And again, we saw this yesterday geometrically, but if we're going to take a vector and multiply it by some scalar, that's going to increase the magnitude by that factor, and that is going to specifically increase the magnitude of each of the components. So it's going to be k times a and k times b. So if I double my vector, it doubles the magnitude horizontally and vertically, both of those components. And then lastly, again, we saw this geometrically. If I have a vector at some point some vector u, or geez, I can't talk. If I have a vector u at some point a, b, then negative u, that would be its opposite, would be at negative a, negative b. Okay, so its opposite would be the opposite direction. So the opposite of going right 4 would be going left 4. The opposite of going up 5 would be going down 5. So we put that negative in there to get that opposite direction. Okay, so hopefully those make sense, and again, this work becomes intuitive. So here, if I have vector u and vector v defined by negative 2, 1, and 4, 3, then I can add u and v by adding the corresponding components. So I would take the negative 2, 1 and add the 4, 3 by again putting together the negative 2 and 4 and putting together the 1 with the 3. So my resultant, right, my sum of these two vectors becomes negative 2 plus 4 is 2, and 1 plus 3 is 4. Okay, negative 2 times u, again, this means I'm going to multiply negative 2 by each of the components of u, which were negative 2 and 1. So if I double my horizontal and double my vertical components, then my resulting vector would be at negative 4 and negative 2. And then here we have a few operations. Right, first it says 3 times vector u, so vector u is negative 2 and 1. And then I want to subtract 4 times vector v, which was at 4 and 3. So let me do the distribution first. If I multiply here and multiply here, triple this vector, then I end up with negative 6, 3. And then I have a couple ways I can handle the next one. If I want to distribute 4 and then subtract, I can do it that way. If I want to distribute a negative 4 and add, I can do it that way. But I want to make sure not to take that negative into account twice. So I'm going to add the next vector by distributing the negative 4. So I'm going to put the negative in here to make a negative 16. And negative 4 times 3 makes a negative 12. And now I can just combine those corresponding parts. So when I add the negative 6 and negative 16, and then, come on pen, the positive 3 and negative 12, then 3u minus 4v becomes a negative 22, and 3 and negative 12 makes a negative 9. And that would be the resultant, right, the resulting vector. Okay? So again, hopefully pretty intuitive. We won't do a ton of that because it's really just sort of basic arithmetic. What I want to show you next is the connection between more of a connection between the geometric and algebraic form, and specifically we need to be able to go back and forth. So back and forth in that if I was to give you the component form, that's the algebraic form for a vector, we should be able to find the geometric form. And remember, in the geometric form what we need is the magnitude and the direction, and then vice versa. If I give you a vector's geometric form, meaning I'm giving you its magnitude and direction, you should be able to give me the algebraic form, which would be the component form. Okay? So I have some formulas that are in the boxes there, but I actually don't think we need those to be able to do this. It will be helpful moving forward to just kind of shortcut the work with the formulas, but let's try to see where these formulas are coming from. Okay? Let's try to do some converting. So number 7 says find the magnitude and direction for vector u, and this is in component form, so this is the algebraic form. When we're asked to find the magnitude and direction, that's for the geometric form. So let's try to figure out what's going on here. Well, we know this algebraic form means we're looking at a position vector that has an endpoint at 3, negative 2. So I'm going to start by drawing this out. Okay, let me make a little graph here. If I make my point at 1, 2, 3, 1, 2, negative 3, or 3, negative 2, that's the end point of this vector u. So I'm going to put vector, let me change colors here. I'm going to put this vector u into my picture right here. Okay, so there's vector u, and I'm trying to find the magnitude and the direction. But think about what we have in this picture. Okay, I know that if I made a triangle out of this, then in fact this makes a right triangle. This is the angle that I would be looking for to find the direction for this vector, and again we're calling this vector u. I know that the other sides of this triangle are going to be 3 and -2 because I moved 3 along the x and -2 on the y to get to that endpoint. So I think we have enough information here to solve, where the length of u is going to represent the magnitude of that vector, and again the angle that's formed by that triangle, that's going to represent the direction. So the direction, actually I'm going to change this color. I'm going to call this vector u. So the direction is going to be given by our theta. That's what I used in green there. And the magnitude, that's going to be given by the value we're going to find for that third side of the triangle, which I called u. Alright, so that's going to be u, technically with our notation, and then our direction again, theta. Okay, so again, I think we have enough information to do this, so it's a matter of, I don't know, what do you want to find first? I would probably find u first. It's the third side of a right triangle, and I could do that pretty easily using the Pythagorean theorem. So I could say that the magnitude of u, remember that's just notation, would be equal to, actually squared, would be equal to 3 squared and -2 squared. So that the magnitude of u is going to be the square root of 3 squared and -2 squared. Or in this case, that magnitude of u becomes the square root of 3 squared is 9, -2 squared makes 4, so that's going to make it the square root of 13. And there are no units here, so I just know that the magnitude is going to be the square root of 13. So that's one piece of my geometric form. Now that's magnitude. I still need the direction, I need the angle, but again I have enough information to do that. So if I wanted to find my angle, I have all 3 of my sides now, so I can use any of them, but let's pretend I didn't solve for the magnitude of u. So just using the given information, if I wanted to find this angle, and the 3 represents the side that is adjacent to that angle, 2 represents the side that is opposite of that angle, I could use the tangent of my angle and write that ratio. So if I wanted to find my angle, I could say that the tangent of my angle is equal to a ratio of the opposite side, -2, over the adjacent side, which is 3, which means to solve for the angle I would have to use inverse tangent. So it's going to be the inverse tangent of -2 over 3. And approximately how much is that? We can find out. So inverse tangent, oops, that's just tangent. Try this again. Inverse tangent of -2 over 3, and we end up with about -33.7. We're in degrees? Yes, degrees. Okay, and radical 13, I guess if we wanted to approximate that, we could. Radical 13 being about 3.6, but I'm actually preferring the exact answer here. So let's go with this as our exact answer, and this could also be approximated at 3.6. So you have both forms there, but the work that we did here would not change if our vector location changed. All that would change would be the 3 and the 2 would become some other side lengths, right? Some other distance along x and distance along y that we're moving. So I could use the same process to solve every single time, which is what we see happening in this first box. If I want to find the magnitude of u, that's what I was doing here, it's always going to be a Pythagorean theorem problem, where I take the x and y components, those are the things that made the side of my triangle here, square them, and then take the square root of that sum. That's going to give me the magnitude of that vector every single time. And then, again, not using the magnitude, but just using the x and y components that you're given, those would always be opposite and adjacent to the angle, the direction angle that we're looking for. So that angle can always be found using the inverse tangent of that. Oh, I put x over y. I totally messed that up. Oh my gosh. How could I? This should not be x over y. This should be y over x. We know the tangent is y over x. I cannot believe I did that. Alright, so make sure you fix that. So sorry. Okay. But every single time, those things are going to hold true. Okay? So we can use the formulas later if we wanted to shortcut. So if I just gave you this, you can go straight to finding the magnitude here and straight to finding the angle here. If you didn't want to draw out the picture, although I think the picture makes sense. Now let's look at where the reverse is coming from. So if I give you the component form, again that's the algebraic form, we should be able to find the geometric form, the magnitude and direction, using Pythagorean theorem and inverse tangent. If I have a vector that's in geometric form, so I give you the magnitude and the direction, then we should be able to also find the horizontal and vertical components, the component form, the algebraic form. So again, let's start with the drawing here. If I was to draw a vector W, put it on a coordinate plane first. Maybe not a quarter plane. I'm sorry, pen. Okay. Sorry, pen. I have pen problems. Alright, so we're back on. A magnitude of 25, a direction angle of 41.7. Just be careful with this. And I put the direction angle up here in the box, but I also mentioned here a direction angle is assumed to be from the horizontal. So like it's an angle of elevation, basically. So a vector that has a magnitude of 25 and a direction angle of 41.7 would look something like this, where from the horizontal, okay, we have a 41.7 degree angle, and again the magnitude of 25 would be here. Okay, so the task here is to find the horizontal and vertical components. So even though our geometric vector isn't typically in a coordinate plane, that's precisely how we're going to look at this. So if we considered it in the coordinate plane, this would be like this is my horizontal, would be the positive part of the y-axis, and then I can go ahead and make a triangle out of this, which would be great because not just any triangle, it becomes a right triangle. And so in this right triangle, if I wanted to know the vertical and horizontal components, that means I would be trying to find the x, right, that's my horizontal component, and I would be trying to find, I don't have enough colors, the y, that's my vertical component. Again, I think I have enough information to do this. So if I wanted to, let's say, use this angle and find x first, x would be adjacent to my angle, and then 25 would be my hypotenuse, and this is going to be opposite. I'll get to that in a second. So I could say that the cosine of my 41.7 degree angle would be equal to my adjacent side over my hypotenuse. So that adjacent side, let me make this generic for a second. What color is that? Black? I can't even tell. So in this case, the cosine of my 41.7 degree angle equal to a ratio of x, which is what I'm calling my adjacent side, and my hypotenuse is 25. So x is going to be equal to 25 times the cosine of 41.7. I said 7 and I wrote 4 degrees. And then again, we could approximate this with the calculator. So 25 cosine, can't see, it's really small, 41.7 is about 18.7-ish, so about 18.7. And again, no units here, so I'm not too worried about that. And then if I wanted to find my y value, again, y is opposite of my angle, so I would use the sine. Remember, the sine of an angle is equal to the opposite over the hypotenuse. So this would be the sine of 41.7 degrees equal to my opposite side is y, my hypotenuse is still 25. So y would be 25 times the sine of 41.7 degrees, which would be approximately 25 sine of 41.7, which is going to be about 16.6-ish. So then I could say that the component form for this vector, let's go over here, component form, I could give this in two ways. Okay, I could say that it's exactly 25 cosine of 41.7 degrees and then 25 sine of 41.7 degrees. Oh, squished it in there. Sorry, I thought I had enough space to do it, but I don't. Okay, now I do. Or I could say that this is approximately 18.7 and 16.6. So again, given the magnitude and the direction angle, which is the geometric form, I can use sine and cosine to find the component form, and that's going to work every single time. Every single time we have our vector's magnitude, that magnitude is going to represent the hypotenuse of the triangle that we can form, right, with that magnitude and that angle. So it's always going to be x and y being the adjacent and opposite sides of the right triangle formed by those two components. So in general, again, that's what we see happening up here. And sorry, let me box this in. I have like ADHD right now, going all over the place. In general, what we see in this box is, again, the reverse. If I give you the magnitude and the direction angle, the magnitude multiplied by the cosine is going to give us the x component. The magnitude multiplied by the sine of the angle, that's going to give us the y component. So that's what we see, this whole thing first in our component form and this whole thing second in our component form. And I just made a big mess of that. But again, we can use these formulas to shortcut the process later, but hopefully it makes sense where they're coming from. Okay, so let's practice using, again, these formulas to look at some geometric forms here and try to write component forms. So I'm going to try to write a component form for each of these vectors. So again, the component form means we're trying to write an x value and a y value, and we just said the formula that the x value would be the magnitude of our vector, in this case it's u, multiplied by the cosine of the angle, and this is the magnitude of our vector multiplied by the sine of our angle. So for this picture, we're going to say this is going to be exactly the magnitude of u. I can see that here. So the magnitude's right here. So we're looking at a 5 times the cosine of our angle is clearly 60 degrees. And then again, magnitude of u is going to be 5, and here we'd multiply by the sine of 60 degrees. And I think we can go a little further than this because 60 degrees is one of our unit circle angles, where 60 degrees intersects the unit circle. Remember, this one is on your left hand, intersects at 1/2 and radical 3 over 2. So this would be technically 5 times the cosine of 60 is a half, and this would be 5 times the sine of 60 would be radical 3 over 2. So we could say that this is exactly 5/2 and 5 radical 3 over 2, and there's no sense in approximating that when we can have that really nice, clean, exact form. But if we wanted to actually put that on a graph, like sketch it out, the position vector, which actually it's already in position there, we might want to approximate those, but I'm going to leave that there, okay? So let's try this next one. Again, it's the magnitude of our vector, which is given to us, right, multiplied by the cosine and sine of our angle to get our x and y components. So I'm going to bypass some of the formula work here. So this one, we have our x component is our magnitude of 6 multiplied by the cosine of our angle, and then it's our magnitude of 6 multiplied by the sine of our angle. Now 280 degrees, not on the unit circle, means this would be our exact answer, so we could leave it in this form, or our approximate answer. Let's see, 6 times the cosine of 280 is going to be about, am I still in degree? Yep, about 1.04. And then 6 times the sine of 280 is going to be about negative 5.91-ish. And hopefully it makes sense. that we have a positive x value and a negative y value because we have a vector that's in position, and we can see that it's in quadrant 4 where x's are positive and y's are negative. Okay, and then I have one more where if you're feeling good, I think this would be a good place to pause the video and try this. Otherwise, let's look at it. So again, if I wanted the component form, and I should be a little more precise here. So this one is called vector u. So let's say u is equal to that stuff. And over here we have a vector that's called vector v. So v is equal to, or v is approximately, let's do that. And over here, let's say w. Alright, so w is going to be equal to, its component form is going to be magnitude of 2 multiplied by the cosine of our angle. Now the angle's not labeled there, but we can see that that's a full 180 degrees. And then it's going to be here 2 times the sine of our 180 degrees. And we can go a little further with that exact form because 180, remember 180 intersects the unit circle at -1, 0. So that means the cosine would be -1 and the sine would be 0. So this would be 2 times -1, and then this would be 2 times 0. And so we end up with a -2, 0. And that should completely make sense. Again, this angle is in position where it's not nicely drawn there, but the initial point is at the origin, and if the magnitude is 2, it's going 2 units to the left. -2, 0 makes sense for the endpoints that's here. That's there. Now you can't necessarily see that endpoint in the first and second pictures, which is why those calculations come in handy, right? But hopefully this one also makes sense, so we can see that directly in the picture. Okay? So we got to be able to go back and forth from our geometric and algebraic forms. We have some formulas we can use to shortcut the process. I hope it makes sense where those formulas are coming from. For now, I think you've got enough to get started on your assignment. But as always, if you need any extra help or have any extra questions, just reach out, let me know. Until next time, take care.